Alright, we're going to go ahead and get started. So make sure that you open up your notebooks to the last section that we were on, solving the string of lights. If you're in Ms. Taylor's class, go ahead and get your Chromebooks on todaysmeet.com/PerlaScience. And then post a message on today's meet. That'll let us know that you're here. And we'll go ahead and get started. Mrs. Richards' class is going to join us a little bit later on today. All right. So going back to our notebook, I'm going to go back to the section we're on. Okay, we looked at parallel circuits. And let's see if I can find page 9 here. So we talked about which design is better. So that's the problem we've been working on. I did switch to page 18. My thing is also there. All right, let me reset my targets. Okay. Use the mouse. Okay. So this is the question we were looking at yesterday. Which circuit am I going to use to build a string of lights? Am I going to use a series circuit or a parallel circuit? Okay. So the thing that I'm going to be focused on today is, oh boy, this is really good today. Oh my goodness. All right, we'll use the mouse. Bring the mouse over here. So let's go back and kind of review a little bit of what we looked at yesterday in terms of these strings of lights. So we looked at some symbols to draw schematic diagrams. We looked at the power source. We looked at bulbs. We looked at motors. We looked at switches. And we looked at wires. The other thing that we talked about was when I build a circuit, I don't ever have curves in my schematic diagram. And finally, I always have to have corners. Okay, so let's take a minute right now and go into your circuit. And I want you to build a circuit using schematic diagrams. Build a series circuit that has 2 bulbs, a motor, and a switch. It's got to be in series though. 2 bulbs, a motor, and a switch.
What about a cell?
Well, and a power source, because it has to be a circuit. Okay, 2 bulbs, 1 motor, 1 switch. And the power source, of course, is a given. What would this look like? There's going to be lots of ways to draw it, but you got to use those symbols that you learned yesterday. So make an attempt to draw this.
Mr. Perla, don't we need wires?
Nope.
No wires?
That's in the circuit. You can't draw a circuit without wires. Okay, so I'm not going to tell you you need wires. You have to have wires. So that's a given. Okay? You don't need it. Okay. set them to it. So what would the power source, that's where I'm starting, what would that look like? Kaylee, come on up. Can you draw the power source?
That's our power source. And we can come down to the motor. And then you would have a switch. And then that ball. And then back to our power source.
Okay. 2 bulbs, a motor, a switch, and a power source. Anything wrong with this? Do you see anything wrong with this circuit? Jade?
No, straight lines. Well, there is some, but not all.
Okay, not all the lines are straight. The lines always have to be straight. Vincent, what else?
The power source, there's supposed to be a long line and a short line.
Okay, power source is not supposed to be the same size lines. Okay, so let me draw. I'm going to draw the same thing that's here, but I'm going to draw it in a different way. Now, I'm going to use the lines that are on my paper here. That's why they're there. Take advantage of it. Bulb. And come straight down. Draw a motor here. Okay, she has a power switch right here, so I'll leave it opening. And she put her other motor or her other bulb right here. Okay. So, pretty close. So, what were some of the things that, some of the differences? Well, the differences was the way the power source looked, and these corners, and not using the lines on your paper. Okay, if you use the lines on your paper, it's going to make your circuits look a lot neater because you're actually following lines, and your lines will look straight. They'll look parallel if they're supposed to be parallel. Okay, so it does make a huge difference. So take advantage of that. Now, let's do one more. Okay, so I want a circuit with 2 bulbs parallel. And 1 switch. And a power source. Now, even though I might not tell you to put a power source, you always have to assume there's got to be a power source in there, right? Otherwise it wouldn't work. So build a circuit with 2 bulbs in parallel and a switch. Who wants to come up and try? Vincent. No, come up and do it. You either know how to do it or you don't. I don't want you to copy it off your book. Okay.
No. Only one bulb's connected to the switch.
Okay. So in this circuit, what do I have? I have two bulbs. Are the bulbs parallel?
Yes.
Yes. Do they have a switch?
Yeah. But the switch
Okay.
is in a lot of places.
All right. Well, I didn't specify where the switch would be, right? But in this case, the switch will only control one bulb. Okay. The other one will stay lit no matter what. Now, what if I said, well, let's build the same circuit here, but this time I want the circuit to be controlled. One switch controls both bulbs. Okay, who could draw that? Kaylee, come on. Okay, in this circuit, would that switch control both bulbs?
Nope. No.
No, it would only control the bulb on this side. It would only control this bulb here. So how do I redesign this circuit? Serenity, come on up and redesign it so that it controls. So just fix it. Erase whatever you need to erase to make sure that the switch controls both bulbs.
No, that wouldn't work.
Okay.
That's one path.
That wouldn't work.
That's one
because
path.
It's not even a path.
Okay, yeah, that one's not even a path. It's not, the power source is not connected on both ends.
You can't.
Can't?
No, you can't.
Okay, Brayden, come on up. Okay, thank you, Serenity, for trying. Alright, so fix it. One switch for both bulbs.
If you're really going to be I know how.
Okay. Would this switch control both circuits?
Yeah.
It would. Okay, so the electricity, once it gets to this switch position here, once the electricity gets to that switch position there, would cut off the electricity to one or both sides. To both sides. Therefore, this switch would turn both bulbs on or both bulbs off. Okay, very good. All right, so let's jump to what we talked about yesterday. Okay, so yesterday we were looking at some circuits. So we discovered that the circuit that we have for the string of lights was a series circuit. Okay, so I'm going to jump back to what a series circuit looks like, which is something like this, which is one path for all of the bulbs. And so once one path was broken, what happens to the rest of the bulbs along that path? They all die. So you told me yesterday that you could find a better way to redesign this circuit. So today what I want you to do is I want you to get your same science materials that you had yesterday. Your bulbs, switches, cell holders, wires, and circuit bases and cells. And build a circuit where one bulb dies, the other one stays on. Once you have successfully accomplished that, I'm going to have you partner up with the team next to you and build a circuit with 4 bulbs. And put those cells together so that you have more power. Okay? Alright, so grab your materials and go ahead and get started.
I'm not standing up this time next year, Carla.
You're not?
Because when I stand up, I intend to have like
That was good.
All right, so Miss Richards' class is just joining us. What we're actually doing right now is building those circuits that the kids think are going to solve the problem of the light bulbs. In other words, what they're looking for is a circuit that if one bulb dies, the other one stays on. Once they have achieved that, then they have a circuit that is successfully able to resist one bulb dying without the other one going out. The challenge then at that point would be for two groups to come together and see if they can build a circuit with 4 bulbs. If one bulb dies, the other 3 stay on. So that's what we're currently working on. If you need any assistance, go ahead and put a message on today's meet, and we could send some students up to work with either room. Thank you. All right, so in our class, we've got the circuits set. We've got some teams that have actually teamed up and built circuits of 4. Please let me know if there's any students in your classroom that are still struggling. We could send some kids from our class to go help. Okay, but we are now up to the next step, our final step here, which is what do they need to be doing? So in your notebooks, I want you to draw a schematic diagram of what you see in front of you. What does this circuit look like? Draw that diagram in your notebook. right, ladies and gentlemen, we are officially finished. Mrs. Taylor's class successfully was able to build these circuits as well. So what we're going to do right now is we're going to go back into our notebooks. And we're going to finish this off. Okay, so let's come back into our notebooks and take the symbols we've learned.
Okay.
And let's extend this. And draw our final design. Okay? So a better circuit design for lights is what? So a better circuit design is to do them how?
Parallel.
Parallel.
Let me write these down.
What does this look like if I were to draw? So I want you to draw a circuit with 8 bulbs in parallel. Draw me a circuit with 8 bulbs in parallel using a schematic diagram. So I know this is my power source here.
How many cells do we need for that?
That just means power source. It doesn't matter. It doesn't talk about how many cells. So I need a power source. I'm going to need a switch. And now the question is, how do I add my bulbs? I want 8 bulbs. So figure out how you would add 8 bulbs to that circuit using the parallel design. Okay. 1 minute to come up with 8 bulbs in this circuit.
I'm almost done.
8 bulbs. So an 8 bulb circuit.
Is it parallel? Maybe use this one.
No. What are you not using? Make sure you're using symbols. Do not draw light bulbs. Not interested in seeing light bulbs. Just draw symbols.
Oh, that's the ball.
Okay, so here we go. I'm going to get you started. And I know that one bulb would look like this. Right? What would a second bulb in parallel look like? Any ideas? Sam?
Maybe like it goes like more out.
Here? How do I hook it up?
It's like a small one.
Okay, so Braden's actually holding it up for me. That's 2 bulbs in parallel. How do I get 8 bulbs in parallel? Okay, what's wrong with yours?
Mine.
Go back to the keys that we looked at. There are no curves in schematic diagrams. So that's 2 bulbs, 3 bulbs, 4 bulbs, 5 bulbs, 6 bulbs, 7 bulbs, 8 bulbs. How do I hook them up? And that's your circuit for 8 bulbs in parallel. I like Braden's plan 3.0. So 8 bulbs in parallel. How many paths does the electricity have in this? How many paths? 8 paths, right? Where are the paths? There's my first path, second, third, fourth, fifth, sixth, seventh, and eighth. So there's 8 different paths electricity can take, which means if one of those paths breaks, there's 7 others. So the rest of the bulbs would never die. Okay? Now if I break the switch, does it kill all 8 paths at the same time?
Yep. No.
Yeah, you'll see that because the switch is here in the front, if I open this switch, all 8 paths die at the same time. So it's important that wherever you put the switch, that's what's going to control. Everything after the switch would turn off. So if I wanted one bulb to stay on and the rest of them to go out, where would I have to put the switch? After the first path, after the first bulb. That way the first bulb always stays on and the rest of them would go out. Okay. Now, some of you discovered something really interesting, so I want to put it up here for you. I want to call it an interesting discovery. And if you're in Mrs. Taylor's or Richard's class, you probably had some kids discover this as well. So what happened? You had a power source, and you had a couple of bulbs, like this. And the students put a switch here.
That's what I did.
And what happened? Well,
When you turn on water.
so let's describe here what happened. It's pretty odd. So when the switch was on, the bulbs were off. And when the switch was off, the bulbs came on.
Why would that do that?
So we had what we call a reverse switch, where the switch does the opposite of what it's supposed to do.
Kind of like a knot game. It's kind of like a knot game.
Let's see. So I'm going to bring a circuit here. Okay. We're going to put a circuit here that hopefully everyone can see. Okay. This is a parallel circuit. We're going to remove the switch from here. And we're going to hook it up. So, I'm going to put it up here so you can see it really quickly. And we'll finish with this. Okay, so what I have is a parallel circuit with 8 bulbs, or 4 bulbs. Let me get this last one to come on. Okay. So I've got 2 cells. With my 4 bulbs. So let me make sure that you can see it. So there you can see all the bulbs are on. But when I add a switch to this last bulb and put the switch at the end, can I have one more wire, Jason, if you have one? Okay. When I add the last wire here, you discover when the switch is closed, the light bulbs are off. When I open the switch, the light bulbs turn on. So it's a backward switch. And so the question is, why does that work? Well, I'm going to disconnect this and I'm going to tell you something about electricity and see if you can figure it out. Okay? Electricity follows what is known as the path of least resistance. Okay, what is resistance? Resistance is anything that slows electricity down. Doesn't allow electricity to travel. Now, what happens when electricity travels through a bulb?
There's resistance.
There is resistance inside a bulb. And you go, well, what do you mean? What's resistance? Well, if you picture a bulb that looks like this,
Can we write this down?
you can if you want.
You don't have to.
Okay, if you picture a bulb that looks like this and you've got the filament in the middle, and you have wires coming out, electricity travels into the bulb. It goes up one of these wires, and it has to go across the filament, back through the filament, and then out the other wire. Now, as it's going across this filament, there is what is called resistance. Resistance means the electricity is being slowed down because the wire is very, very, very thin. And so all the electricity that's having to go across that very thin wire, it can't get through there, and it's being slowed down. Picture an entire classroom all trying to get through a tiny little doorway at the same time.
Oh.
Would there be resistance? Would kids be smashing into the sides of the door?
Yeah.
Yes, you'd be smashing into the sides of the door. Now, the same way that if you take your hands together, put them together, and rub them back and forth. Okay, so take your hands, put them together, rub them back and forth. Okay? What you'll discover is you have resistance between your hands. Your hands are not wanting to do this, but you're forcing it to. What are you feeling?
Resistance.
You're feeling heat. So,
Oh my gosh, it's so warm on your face.
as the electricity is going across that filament, there is resistance, which means that that wire starts to get hot the same way you move your hands. Eventually, that wire gets so hot that it glows, and that's the light that you see. That's what causes light. Now, there's a lot of resistance in here. Electricity doesn't like resistance. Electricity would just love to go back to the cell without having any challenges. So, electricity will always take the path of least resistance, where it can find the least amount of resistance. So if it could get back to the cell without having to go through any resistance, that would be perfect. So take a look.
Is there resistance in
Take a look at this circuit one more time. When I plug this in, and the switch is off, there's only one way for the electricity to get back to the cell, and that's to do what? There's only one way for the electricity to get back to the cells. And what does it have to do? It has to go through the bulbs. It's going to leave here, and it's going to go that way, and this way. The switch is open. It can't go through the switch, right? So the only way to get back to the cell is to go through
the light bulbs?
through the bulbs. So it has to go through resistance. It has no choice. There's no other way. It has to go through resistance. Watch what happens when I close the switch.
It turns off.
When I close the switch, now there's an option. It can either go through the bulbs or go through
It's the switch.
the switch. Does the switch have any resistance?
No.
No. The switch is like a wire. So right now the electricity is still traveling, except this time it's going through where?
The switch.
It's going through the switch. And it's ignoring everything else. So the electricity is traveling. It's going through this path, through the switch, back around, and it's ignoring all the bulbs because the switch is the path of least resistance. When I open the switch now, there is no path of least resistance anymore. The only path is
Bulbs.
through the bulbs. And so it will go through the bulbs. Okay? And so when you encounter something like this, always remember, say, why is this happening? Oh, it must be the path of least resistance. Okay? So, if I ever ask you, can you build a reverse switch?
Yes, we
Yeah.
can.
Make it go through the bulbs, make it go through a motor, and then hook up the switch directly to the power source. And the electricity will always go through the switch only and ignore the bulbs or the motors or whatever it is that you put into the circuit. Okay? Alright. So that's the answer to that. Alright, so we're going to get ready to close out. So let's just go ahead and wave goodbye to Ms. Taylor and Ms. Richardson. Thank you for being with us. We'll see you tomorrow.
Peace.